Hi, welcome all. And today we are going to see a topic in 5th unit, that is reflection of plane waves by perfect conductor. Okay. So what do you mean by reflection? So when a uniform plane wave travels from one medium to another medium, and these two medium have different intrinsic impedances. So in this case, reflection takes place at the boundary. Okay. So when wave travels from one medium to another medium having different impedances, reflection takes place at the boundary. Okay. So the part of the wave is transmitted in medium B and remaining part is reflected back. So there is a part is transmitted, another part is reflected. So there are incident wave, transmitted wave, and another one is reflected wave. Okay. So depending on the manner in which the uniform plane wave is incident on the boundary, there are two cases. One is normal incidence and oblique incidence. Normal incidence mean the incident wave is at 90 degree to the plane. Okay, oblique incidence means any other angle apart from 90 degree. So there are two types of incidences: normal incidence and oblique incidence. And also when a uniform plane wave travels from one medium to another, so reflection takes place. A part of the wave is reflected, another part is transmitted. Okay. So normal incidence means when the uniform plane wave is incident normally, that means perpendicularly or 90 degree to the boundary between media, it is called normal incidence. Oblique incidence means when the uniform plane wave is incident obliquely to the boundary between two media. Oblique, it is called oblique incidence. Okay. So now let us consider the normal incidence in perfect conductor. So we are going to see normal incidence in perfect conductor. So in a perfect conductor, there is no absorption of energy. So all the waves are reflected. So when the plane wave incident normally upon surface of perfect conductor, the wave is entirely reflected. So upon the conductor, so if it is a dielectric, there will be some absorption. But in the case of conductor, the wave is entirely reflected. And there can be no loss within a perfect conductor. There is no loss within a perfect conductor. Run of the energy is observed. So as a result, the amplitude of E and H in the incident wave are the same as the amplitude in the reflected wave. And they are out of phase. Okay. So here when we see the incident wave have this phase and the reflected wave has this phase. So these two are out of phase 180 degree, but the amplitudes are the same. That means EI equal to minus ER. EI equal to minus ER. Okay. So the electric field of incident wave is EI into e power minus gamma x. Gamma stands for propagation constant and x is the distance, of course. Okay. And the reflected wave is ER into e power gamma x. So since the incident wave and the reflected wave are out of phase, so we have reversed the sign. Here minus gamma x, here plus gamma x. Okay. Since alpha equal to 0 for a conductor, so since alpha equal to 0, for attenuation is 0. For a conductor, the attenuation is 0. Alpha stands for the attenuation constant. So the attenuation is 0 for a conductor, and so gamma equal to alpha plus j beta. So if alpha equal to 0, gamma will become j beta. Okay. So now the incident wave can be written as EI into e power minus, so replace gamma with beta. So minus j beta x since alpha equal to 0. And the reflected wave is ER into e power j beta x. So the resultant electric field is a sum of electric field of incident and reflected wave. So there are two waves. One is incident wave, another one is reflected wave. And the incident wave, that is resultant wave, is a sum of these two waves, incident waves and the reflected waves. Okay. So this is a resultant field. So ET of x is a resultant field, which is the sum of the incident and the reflected waves. EI e power minus j beta x plus ER e power j beta x, since these two are out of phase. Okay. So but EI equal to minus, the amplitudes are the same and inverse. Okay. So the EI equal to minus ER. So we can replace it as EI into, so here we can replace it with minus EI. So we have EI into e power minus j beta x minus e power j beta x. So this e power minus j beta can be written as cos beta x minus j sin beta x. So here cos beta x plus j sin beta x. So minus into minus, minus into, so within bracket, so both signs will become minus. So these two terms are getting cancelled. So we have ET of x as minus 2j EI sin beta x. So this is the expression of the resultant wave in the case of reflection by a perfect conductor. Okay. Similarly, so this is with respect to time variation. So the ET of x comma t, when you add a time variable, ET of x comma t equal to minus 2j EI sin beta x into e power j omega t. So with regard to time, it exponentially decays. Okay. If EI is chosen to be real, it can be written as
So Et of x2 equal to minus 2. So if we can consider it as a real, so take the magnitude component alone. So it is 2 ei sin beta, real part alone. So it is 2 ei sin beta x sin omega 2. So neglect the imaginary term. Okay. So this is obtained. So I have written here. This is obtained. There is minus 2 g ei sin beta x into j sin omega t. So here we have written only j sin omega t. So when you multiply, this minus of minus become plus. So we will be having e sin beta x sin omega t. Okay. So the above equation shows that the incident and the reflected waves combine to produce standing waves which do not progress. So this is called the standing waves. So how do you define standing waves? The incident wave and the reflected waves combine to produce standing waves which do not progress. So these standing waves will not progress with respect to space. So they are called the standing waves. Okay. So similarly we can derive for the magnetic field. So here the magnetic field must be reflected without reversal of phase. So here there is no phase reversal takes place in the case of magnetic field. So Ht of x equal to Hi. So here we need not change the time. We need not change the sign. So Hi e power minus g beta x plus Hr e power j beta x. So Hi into so much. So 2 Hi cos beta x. So there we got sin beta x. So here we got cos beta x. So expressing in time variation, it can be written as e power j omega t. And if Hi is chosen to be real, again we have 2 Hi cos beta x cos omega t. Okay, where we have Et of xt as 2 ei sin beta x sin omega t and Ht of x comma t as 2 Hi cos beta x cos omega t. So we are able to arrive at the electric field and magnetic field expressions for reflection of plane waves in conducting boundary. Okay, the above equation shows that the magnetic field H has a standing wave distribution. It indicates that E and H differ by pi by 2 in phase. So there is a phase difference existence of E and H by 90 degree. Okay. So this is with this we have concluded. So in this lecture we have discussed about reflection of plane waves in conductor. So and as far as conductor is concerned, so we have considered the attenuation constant alpha equal to 0. For a conductor, attenuation is 0. And another thing we consider is that there is total reflection. No energy, there is no energy loss inside the conductor. So whatever be the field transmitted is reflected. Okay. So we have ER, EI. So we have ER and EI, no ET. Okay, and we have derived expressions for ET. So that is resultant field ET and the resultant field HT. And we have arrived at the expressions of 2 Hi cos beta x cos omega t and 2 ei sin beta x sin omega t. Okay, with this we conclude with this topic. And the next class will discuss about reflection by perfect dielectric. So what will be the difference? So their case we cannot consider that what the total energy is reflected. So we have to consider that portion of the energy is lost. Okay, so is transmitted. Okay, so that means there will be transmitted wave, incident wave and reflected wave. So next we will discuss that in the next session. And questions I would like to ask: what do you mean by normal and oblique incidence? So if the incident wave is normal to the boundary between two media, surface of boundary, that is called the normal incidence. If it is oblique, it is called oblique incidence. What are called standing waves? The combination of incident waves and the reflected waves is called standing waves. And as you know, they do not progress. They do not progress. They will be standing. So they are called standing waves. And another questions may be asked is derive expressions for electric field and magnetic field. So we have arrived at expressions of Et of x comma t and Ht of xt. Thank you.